So welcome everyone to this new appointment of the 40 under 40 lecture series on combustion. Today we actually are very pleased to welcome Professor Leo Xiaohang Fang. He's an assistant professor at the Schulich School of Engineering. This is the University of Calgary, and as well a visiting academic of the Thermal Propulsion System Research Group at the University of Oxford. He received his bachelor from the University of British Columbia and the PhD in engineering science from the University of Oxford. He has a wide range of interests, including turbulent combustion, of course, high fidelity simulations with detailed chemistry, as well as novel computational diagnostics tools. He is currently leading a hydrogen center of excellence on hydrogen gas burners, which is supported by the Natural Sciences Engineering Research Council of Canada. Today, Leo, we talk about model development and hypothesis testing for partially premixed flames. Again, thank you, Leo, for accepting our invitation to do this so early for you. And I give you the floor for the presentation. Thanks again.
Thanks for the invitation again, and then I'm very privileged to be here. So today my topic is model development and hypothesis testing for a partially premixed flame. So this is one of the model that we worked, and then that I think it was a little bit introduction to the community, and then obviously it's standing on a lot of other researchers that we worked with closely, including my mentors. Before we start the actual presentation, I want to introduce where are we. So Canada is actually very, very big. So we are somewhere near here. I would say middle, but towards the left side, towards the west coast of Vancouver side. And then we're the largest city in the province of Alberta, and then third largest city in Canada in terms of like metropolitan. This very, very interesting part for our province is that we have one of the biggest energy centers in the world. And then we are sometimes ranked as the top 10 most livable city because of the picture of the year. So if you ever drop by to visit Canada, and this is probably one of the places you want to visit, and then you will probably land it in Calgary for this place. And then I'm sure you might be familiar with this. This is from Windows protection screen, I think. So this is Banff National Park. So in terms of university, we are a public research university in Calgary, Canada, and then it's a U15 member. U15 in Canada stands the 15 university that has a significant research capability and research funding. And we have very, very close tie to the petroleum and geoscience industry with lots of opportunity in the energy sector. The simple reason for that was because we are very, very close to oil sands. I think, if I'm correct, we have one of the biggest oil reserve in the world. And then we have a recent opening for an energy transition center. And then we are actually hosting the not next, but this Combustion Institute Canadian sector spring technical meeting in May. So if you are interested, the registration is still open. So come visit us if you can, or in the future as well. So a little bit about my research group and then my previous research. So there are three, generally, I would say quite broad topics. One of them is turbulent reactive flow theory and modeling. So this is the core of my research group, which relates to chemical source modeling and turbulent chemistry interaction and conditional moment closure approach or conditional moment closure related approaches. So one of the cases we were implementing was for Converge to adapt turbulent chemistry interaction model called conditional source term estimation that is relevant to conditional moment closure. And then this was a spray A case that we did as a benchmark for the capability of the model. And then recently we have been developing a few other things that is relevant to the industrial relevance of where I am at the moment. So one of the broad topic is called computational diagnostic tools. One of the methods that we are furthering with the help of the original designers is the chemical explosive mode analysis. We are assisting the high fidelity simulation we get from our collaborators to see if we can use computational diagnostic to dissect interesting physical phenomena in a large data set. And also we have precursor detections for combustion instabilities. I personally is not a thermoacoustics person, but we happen to work with experimental groups near Calgary because we have industry projects that is relevant to burners, and then there are instabilities that was diagnosed by let's say OH chemiluminescence or a lot of experimental techniques. So we're developing techniques such as manifold reduction techniques to detect abnormal combustion detections. So in the particular case on the right side, this is the spectral pod analysis for a burner that we had, and we're trying to detect through the OH chemiluminescence image of what is the excitation frequency of the instability of this particular burner. So the last bit was some sort of adventure I did during my postdoc because we had this project with Supernoc, and where I touched a little about detonation, and recently we got some support for designing detonation arresters. So our group is doing reduced model simulation or a calibrated routine for studying large simulations on deflagration to detonation transition, as well as quenching or reinitiation of detonation. I would say this is a very, very new topic that my group is working on, but we're glad that we're working with some leading experts on this field. So that was the case for my research group. So in particular for this particular talk, my focus will be mostly on the first topic, which is turbulent reactive flow theory and modeling, and then specifically introduce one technique we think it's suitable as well, and maybe as an alternative for doing partially premixed Fang. So a little bit of background. I'm sure a lot of you probably knows quite well, and probably better than I do anyway. So in this particular case, what is the turbulent reactive flow modeling? In a particular CFD solvers, we would have transport equations for Navier-Stokes equation, energy and mass, etc. And then if we go with a symbolic form of Favre average species transport equations, we can roughly divide a couple things into this, into the entire system of equations. For example, we have the rate of change of term, and then we have the convective term, and then that should roughly equal to the diffusion term as well as the chemical source term. So the focus of what I was learned and my research is about the closure of this term. It's called mean chemical source term. So why is this term fairly important? Because an explicit series of expansion of the mean chemical source terms might not be viable because it is highly nonlinear and it's very sensitive to truncation, and then it needs a lot of additional closure to cater different terms that we include when it's a higher order. So what are the options that is available, and then that has done a lot of attractions, and then why this is difficult. So the difficulty part here really, when we call chemical turbulent chemistry interaction, is because there are different scales that we're trying to solve. So let's say for a physical system, so on the left side, we have a physical system. In this particular case is a reacting flow system. On the left side, we have the chemical time scale, which means that for a methane burning, for example, there are different type of chemistry that happens at a very, very fast time scales, and then some of the chemistry that really have very, very slow chemistry, slow time scales. For example, the NO formation, which is always a challenge for simulation, for turbulent reacting simulation. So obviously, because it is a flow, so that means we also have to cater flow, turbulence, and diffusion timescales. And this is relevant to non-reacting flow simulations, for example, the approaches for closing turbulence terms. So the idea here really is that if we kind of want something that is to be as accurate as we want, we probably want to resolve in this line, which we can resolve everything about the chemical time scale, and then we resolving everything about physical time scales, which means it is a bit of a challenge, but we will receive something that is probably in a good accuracy. And then this is usually where DNS lands. But in reality, because if we are designing an industrial burner, or if we are designing an industrial product, so at least from my experience here, is that most of the industry partners are using techniques that is relevant to the RANS scale, or some of them is in largely similar, largely simulations range. So in that particular case, we will be resolving somewhere near this range, which means how do we account for the interaction between the chemical and as well as the turbulence scales is a bit of a challenge. So this is what we are focused on, which is called turbulent chemistry interaction models, and then see if we can have a better model for different conditions that is this flame is running at. So there are a lot of the options available, and then there are options that has been around, and then there are a lot of development for each stream of this. I'm just going to do very brief introduction of some of the techniques, but obviously there are a lot of other options or a lot of the advancements around these topics. So first of all, for a lot of us that using OpenFOAM or using Converge or using ANSYS, I would say. So one of the very well established model or is well used model is called well-stirred model. So what this does is assume that it's infinitely fast mixing compared to the chemical reaction timescale. That means that whenever you do a cell calculation, you already assume that the turbulence has already well stirred this cell, and then you would have a well stirred composition that you are taking into account, which it can help to understand the combustion itself, which means that the advantage here is that you can incorporate detailed chemistry, and you can do a direct integration approach and evaluate the mean reaction source. So in this particular case, there are some advantages here because obviously it is widely used. So you will see this quite often, and it is probably integrated quite well with a lot of the software. But in this particular case, you might only have the first order moment, which I will explain what does that entail, or the mean of the scalars are considered. Obviously, there are a lot of other models that advancements built on top of this. So for example, partially stirred the reactor and et cetera, et cetera. But I'm not covering that part for my talk. So the second thing that I think a lot of you or and then a lot of us have been used, I personally have used as well, is a flame rate models. So assume that a dimensional turbulent flame can be represented by an ensemble of laminar 1D flames called flamelets. And then you can use representative 1D configurations to choose between turbulent flames. So there are counter diffusion, and then there are premixed flamelets that you can represent it. And then you can use scalar evolution in these 1D flames, and then can be used to characterize the scalar evolution in a turbulent flame. And then obviously, again, there have been a lot of advancements related to this, and then they have been used widely in various flames and very, very successful and very, very good results. So for me and my group, we use a different approach, slightly different, and obviously this is not a new approach as well. So we're just gonna slowly introducing this idea. If you're not familiar with it, it's called conditional moment approach. So what we really care is something for simulations that not fully resolved. So if you think about the scale graph, we're not reaching to the scale that is fully resolving chemistry and fully resolving turbulence. So we cared about simulations that's relevant to RANS and large eddy simulations. So what has been found is that using the first moment might not be accurate. And then the idea here is that we would want to use a conditional variable to actually approximate this term with the assumption that the conditional average does not fluctuate too much. Okay, so how do we explain this? So if you're looking at the right graph, assuming that this is the flame that you are simulating, for example, and then this is a grid. So this is a representative grid that you had in LES. So imagine you're setting up an LES simulation, and this is the grid. And then this is the finest resolution that your grid is actually solving. But magically, at the periphery of the flame, we happen to know this DNS. We happen to know the DNS exact result for this entire flame. So which means that you're looking at this grid, and then this is what actually happens underneath it that your solver does not know. Okay, so if we're using a first moment variable, let's say if it's Arrhenius type chemistry approximation for chemical source term, we're using the average value for the temperature, average value for the mass fraction, average value for the density at this particular grid to get our reaction rate. So what does that entail? So if you plot this, for example, the mass fraction of the water at this particular grid. So in reality, there are things in this grid that was fully burned, and then there are partially burned, and then that doesn't even have any water content because it's just pure air. So if we do an average position, that means that we are using this red dot information to approximate the entire chemical source term along this entire grid. So that might be problematic in that sense. Why is that? It's because that we know that this term is highly nonlinear. So if you're using an averaged value to approximate the chemical source term, we might get a value that is quite off compared to what we want exactly, especially, for example, for the well-stirred reactor idea is that we're assuming that everything is already stirred, which means that we're assuming that everything is already at this red dot. But in reality, if you look at the 4DNS results, we're thinking about maybe that's not an accurate representation, at least for this particular grid. So what can we do then? So usually what happens that, for example, if this is a non-premixed flame, so what we would do is we would do a conditional variable. What does that mean? Is how about we plot all the points that is relevant to the mass fraction of the water or mass fraction of any particular species on the condition of some variable that is very important to the formation of this particular species. In this particular case, it's called mixture fraction, which is the same approach that Flamelit and a lot of other models are using. So what does that mean then? In this particular case is that if you are actually plotting the mass fraction along with the conditional variables, you can see that now we can probably have a kind of a scientific way to saying that this is a good approximation to say that there exists a functional representation of this value on the condition of a mixture fraction. So this is what we called, we are using the first moment closure method. So then we can say that maybe this is a good approximation for it. So this is what we started with the conditional moment approach. And then obviously the challenge then come for any single particular field here. How do we get these values, right? Because if we want to approximate it, we still assume Arrhenius type. And then how do we actually get the values inside this bracket? Because chemical source term is a function of these values. So one of the thing here is that conditional moment closure. The easiest way to think about this is that how about we just transport the conditional variables, and then because it's a simulation, you can basically transport anything that you want, and then you can basically transport anything that you can create any variable, you can transport it in the flow field as long as you preserve these laws that is conserving the mass, conserving the momentum, conserving the energy, and then conserving the species for combustion simulations or turbulent reacting flow simulations. But obviously the challenge here is that when we trying to close this, there will be a quite lot of terms that is happening here. And obviously because you are adding a lot of transport equations, so it might be a bit computational expensive. And then obviously this is a very well-known approach, and then there are a lot of new development here. So I'm not gonna elaborate too much, but that's one way of doing it. So what our thought was when, so this came from my previous advisor, Kenneth Bush. So we know that this is what we don't want for a particular flame, especially for the one that I just showed. And then we kind of know that this is approximation. So we also know that, okay, from a previous time steps, in order to run a simulation, you probably have an initial condition, or you have already ran the simulation at the beginning of the time steps. You prescribe an initial condition at least, which means at the previous time step, you would know exactly from the CFD solver that what is the unconditional value of this, right? So then if we know the relationship between statistics of this conditional variable, we know that the conditional variable times the statistic of this conditional variable with the integration should get you the unconditional value. So in this particular case, then, if we magically know the statistics of this conditional variable, then all we have equation is ax equal to b, which a represents the statistics of this conditional variable, b represents this unconditional value that came from the CFD solver, and then all we have to do is to find x through an inversion. What does that mean? We can, instead of transporting this x, which is quite a lot of work, what we can do is we can do x is equal to b times a minus 1, because that is just a matrix inversion, and you can get the statistics quite easily if you assume this is the statistics that we can presume. So a real routine that is going to happen for this type of combustion model, which is called conditional source and estimation, then is that we have a CFD module, which we insert the conditional variable. So in this particular routine, it represents a non-premixed flame. So we would introduce a transport equation for mixture fraction. We then introduce a variance for the mixture fraction. And then we can presume the PDF based on our knowledge. In this particular case, for non-premixed flame for mixture fraction, it's usually used a beta function, like a lot of other models. And then we will get the unconditional value from the CFD module for every routine. Or if it's an initial routine, we will get it from the initial condition we set. So then we use this CS routine. What the CS routine really did was that it's inversion. Obviously, because it's a yield post problem, so that means that we need a lot of regularization, and then we need a decomposition to actually find out what is the conditional variable. So once we get the conditional variable, we can build a chemistry, just like approaches, for example, PDF methods. So we can build the chemistry, and then we look up the unconditional variable. Conditional variable of the chemical source term. Once we get the chemical source term, we use this presumed PDF once again to integrate it back to a chemical source term. With that part, we can actually go back to the CFD solver, and that means that in particular, we can have a closed loop of it. Entire combustion model, which includes the chemical source term estimation, and then which means it includes this hypothesis. So this is the essence of the conditional source term estimation. It's a little branch that my advisor started, and then we have been working on this together with a few other academics to close the chemical source term with this particular hypothesis. So how do we actually implement this? So in this particular case, we did pre-allocation of the conditional source term estimation for the cell prior to the runtime. And then we did a bit of overlap of the ensemble, which means that we want to eliminate a little bit of discontinuity. And then for each ensemble is assigned to one processor, ideal for flame with clear symmetry. This particular case, obviously, it's a jet flame, so we can assume that. And this has been successfully implemented in Sandia methane coal flames, including CDEF, where extinction becomes a bit more extreme. And so one of the things that we had here was obviously the inversion, because all we really cared was the conditional value here. And then in this particular formation, it is not about mixture fraction, it is about progress variable. So it can be used for both premixed and non-premixed, which means you can actually do the inversion, and then you can use this regularization of Tikhonov regularization. We want to explore a few more regularization in the near future as well, because we might find there are more developments in linear algebra that is probably way better than what we have done before. And then we can reduce the matrix through some matrix manipulation to regularize it and to reduce the size of the matrix when we do the inversion. And then with a little bit of decomposition, we will get what we want, which is the conditional variables to achieve. So with that, we can sort of do lookup of chemistry. So this is similar to what PDF method would do. So in this particular case, previously, they have used TGLDM, so trajectory generated a low dimensional manifold, so which we are using CO2 and H2O as a representation of the entire manifold. And then we can do the separation of the time scales in chemical reaction source terms, and then we do lookup, and then we use mass fraction of H2O and CO2 as the progress variable. So these are all developed before. But the challenge really here is that if you look at the successful implementation, at least before my PhD, so most of these studies are actually relevant to methane only, and then there are one more study that is relevant to N-heptane, but it's a priori study as well for CSE routine. So my PhD really resolved in a way is that can we improve this, because we had find the challenge of using chemistry of TGLDM a bit more challenging with complicated fuels or with more higher carbon fuels, because the trajectory will cross over and it's very, very hard to actually for us to construct something that is based on TGLDM for a higher carbon fuel. So in this particular case, during my PhD then, I was thinking about we can use the conditional moment hypothesis, but how about we use the chemistry advantage of a flame generator manifold? Because in essence, what we are doing is that we need a chemistry model, but if we are already reducing the conditional fluctuations, we might as well assume that when the conditional fluctuation is very, very low at this particular point, we are assuming that this is probably as close as to a flamelet model that can that is accurate, very, very accurate. So in this particular case, then what I have done is that I incorporated FGM not as a combustion model, but really as a chemistry lookup table to resolve the chemical to get the chemical source term directly. And then we use the CSE routine to close the turbulence chemistry interaction. So that was what my PhD was about, and we developed something that is a CSE-FGM approach, and then to enhance what this approach can do for higher carbon fuels, and basically eliminating the hurdle of using CSE on a higher carbon fuel. So this has been quite successful. So we are actually able to capture this flame, which a lot of you are very familiar, with a very, very low resolution grid. In this particular case, this entire simulation is only about 1.2 million cells in particular. And then we're able to characterize the view very, very good in terms of the comparison. And then also, probably more interesting here is that we are able to capture reignition and extinction, and then the scalar dissipation rate effects on this flame in particular, because we're transporting Z and we're transporting Z double prime as well, and it's quite easy for us to do a little bit more study on scalar dissipation rate as well. And then recently our group did a bit more detailed studies on computational diagnostics relevant to the end of injection, which is a missed piece in this particular flame. So where we are studying how do we how do we analyze this particular spray, and what is the propensity of it to travel back at the end of injection during each cycle of the engine. Okay, so this is a bit of introduction to what our approach is. So I'm trying to go further to really what this topic is and what we are doing. So for conventional modeling, so for a lot of the studies that I have presented just before, we mostly catered one particular type of flame. So in this particular case, we say perfectly premixed flame, which means the conditional variable is not that bad. We can choose progress variable. And then the second part is non-premixed flame. So in this particular case, we choose mixture fraction for spray A. But what happens if it's a more advanced systems for, let's say, stratified or partially premixed flames? How do we cater this? So a very, very simple way to think about it is that maybe we should just directly incorporate a mixture fraction and progress variable. But really the question here is that, before we do any model development, the question we really should ask, is that a right route? And then how can we say that this is the best way to develop a new model? So this is a concept with what would the challenge that is actually relevant to this. So first of all, remember in the conditional fluctuation, which I will explain a little bit later as well, is that in order to use this conditional moment approach related approach, we have to say that we can neglect the spatial gradients of any scalar. And then the second question is that if it's a partially premixed flame here, how many conditions do we need for this partially premixed to have this assumption that this spatial gradient is actually very much minimal? The second question we have is that for conditional variables for different flames, right? So mixture fraction is probably well known in this community that, okay, it is probably, with Bilger's definition, it is probably good for non-premixed flame. The second question then, it comes to how about progress variable? Like if we go to the literature, there are quite a lot of definitions for progress variable, especially when we are using, let's say, endodecane or heptane, or a more realistic field that we're using for liquid propulsion or liquid energy. What are the appropriate assumptions that we use, and does it really matter to use what type of definition of progress variable in this particular case, or for our model? The last one is that if we are using two conditional variable, for example, the idea here is that we are doing twice of the integration, and then we kind of have this probability density function. But if it's a statistical approach, and then if we're assuming that these two variables are actually statistically independent, then it's probably okay to say that the joint probability density function of these two variables are the products of their marginal PDFs. But in reality, if, for example, we're choosing mixture fraction and progress variable, can we actually really say that this is a statistically independent variable, right? And also, what is a good PDF for progress variable? I don't think we have a consensus within the community as well. So that's one of the things that we kind of want to touch around as well. So in order to solve these couple questions, then we're thinking about how do we do this? So the hypothesis really comes in the question one is recall that the conditional average does not fluctuate too much in space. So our study really starts with the question of what is too much, and then what is the definition of too much. So for example, if I took a random LES grid and then I take out the DNS results and then I just plot all the values, imagine that the green line and the red line represents the low value and the high value of this particular scalar. And then in our model development, we assume that the black line is where the function relies on. So if we have a bit of fluctuation, let's say, for example, this figure on the left side or this figure on the lower quadrant, we will say, okay, maybe the conditional fluctuation is not too high, and the black line is a very, very good representation of it. But what happens if we have a grid that actually fluctuates so much? Can we still say the black line is actually a good representation, which means that is the conditional fluctuation or conditional moment approach based on this assumption still valid? So that was the question that we first thought, and then obviously most of the work for this part was done by my advisor, Kenneth Bush, and we just had a bit of discussion during my time in Oxford. So what we thought about, first of all, is that is it valid to neglect spatial gradients for partially premixed flames? And how many conditions do we need for partially premixed flames to make this variation a little bit small? So when we thought about this, obviously, ideally, we would have a lot of DNS for various flames anyway. But in this particular case, we thought about there are actually enough experimental data in the community. For example, we have a lot of measurements for Sandia D flames, and we have Sandia C, Sandia D, Sandia E, Sandia F, which includes a jet flame that was low or none extinction to little and to moderate to intense. How can we just really treat this entire flame as a conjunction of a huge data set or a very much a DNS itself, and then just to directly study the conditional fluctuations based on this? And then maybe we can get more interesting results anyway, because that will actually, if we assume the experiment is done very well, which it should be because it's a very, very well-known data set that we're doing a lot of benchmarks. And then we can treat this for our hypothesis testing. So what the result then? So in this particular case then, what has been done is that if we do the local average of the conditional fluctuation of the species, mass fraction species for every one of the species, around the conditional average, for let's say Sandia D alone, only use mixture fraction as a single variable, conditional variable, and we are collecting all points at the radii together, and we plot a function of the radii and axial location. So in this particular case, how do we read this? Is if you look at this is the radii, so this is the spatial location on the 2D flame, 2D axis. And then what you're looking at this is that the fluctuation of the CO2 is actually very, very small, at least further downstream of the flame. There are something that is happening here because we had a discussion with the experimentalist as well. So there might be some fluctuation in the experiments anyway at the exit of the flame. So that might be the trouble here, and that we are seeing that it's not really consistent. But the idea here is really, if you look at the scale of this is 10 to the -3 anyway, which means that it is probably an okay assumption for something to be conditioned with one conditional variable for at least a Sandia D flame. So which means that it's not too much of fluctuation of using CMC type of approach for this particular flame at least. So how about we combine C and F? Because if you combine the flames from C to F, that the idea here is that we're actually thinking about a flame that transitions from low extinction all the way to high extinction, which means it includes a partially premixed assumption. So then if we do that, if you think about, okay, now our hypothesis is that for partially premixed flame, all we need is 2 conditional variable. And then in order to make this assumption right, this fluctuation should be small as well. And then in reality, yes, it's actually much smaller if we use anything that is 2 conditional variables. So in this particular case, the way to look at it is that we saw the scale of the fluctuation is actually orders of magnitude smaller if you use conditional variable. It's 2. So the physical insights of this really is that in reality, when you do a simulation of a partially premixed flame, even if we don't know the spatial location of what's going on in this flame, if we know a particular location's mixing state, which is described by the mixture fraction, and then if we know how much this has burned, which is described by Proc's variable, which pretty much says that we can actually describe everything that is relevant to the thermochemical states of this particular grid anyway. So that assumption or this type of validation is not only obviously applicable to conditional system estimation or CMC type of approach, but also helps validation as well for flame-related research if it is using multiple conditional variables. So that was an interesting start for us to do this. And then obviously there are a lot of findings that I just said, which means that a single conditional variables vary a little bit significant at the downstream direction, which is close near the nozzle that we meant downstream. And using a single and global condition for flame D might still be acceptable. And then this analysis for CNF also indicated that the conditional fluctuations do not exhibit any significant dependence. And bear in mind, this is different flame and with different Reynolds number. So that means that Reynolds number actually doesn't even play too much of a role as soon as we know what's going on with the mixing state and then the progress of the flame at this particular location. So in this particular case, then we will say, okay, maybe we probably at least need 2 or maybe 3 if there's, let's say, a bluff body, because in this mixing conditional variables, we didn't include anything that has heat transfer because that was not included in this particular thing, right? So that is one of the very big study of assumption that my advisor previously did. And then the second part that we did, then just following on this, is what are the best conditional variables for the flames, actually. Now we know that, okay, for a partially premixed flames, yeah, we probably need at least 2 conditional variables. But how about what are the conditional variables, or does it really matter? Right? That was always the question that we had, is that a lot of studies trying to very hard to find a progress variable that is a good definition and then make sure that they can be used for a particular flame. But our question really for our particular model is that does it really matter actually? So we have the fortunate enough to get the data set from this Cambridge Sandia swirl burner with the characteristic of premixed and moderately stratified and highly stratified. Again, in this particular case, it's representing a lot of partially premixed characteristics. And then same with the Sandia flames. One of the things we thought about is that, first of all, it's a very simple technique, and I'm sure Professor Prente would have a lot more knowledge than I do. But when we think about this, we had a bit of a discussion, was more like, if we are representing this flame with two physical phenomena we thought is dominant in this flame, the characteristics of this particular flame using the principal component analysis, a simple principal component analysis, should really align with what our hypothesis is. So the idea here is really that if we're doing a data manifold reduction techniques through principal component analysis, the principal component 1 and principal component 2 should somehow align to mixed refraction and progress variable. Otherwise, our assumption will be pretty bad, because that means that how is it possible that we are not even describing the principal direction for this data set? With two variables, we believe is the most important part for this flame. And then the results really is actually quite interesting in this particular case, is that yes, actually, if we do a very simple progress variable and then principal component analysis for this, it's actually aligned with mixture fraction and progress variable, very much aligned together. And then one of the idea here is really then, if we do this particular thing again for the same paper, we tackle one more question that we have, is that how about choosing different type of progress variable? Would it make a huge difference? The way to look at this is that we chose one particular progress variable alone to see the conditional fluctuation of this. And then we choose two different type of combination, which includes progress variable and mixed refraction. And then in this particular case, we found that it's actually very hard, and it's kind of arguably difficult to say which progress variable definition is going to help a lot more for fluctuation of RMS. But it is actually quite evident that if you use two conditional variables, your fluctuations will be very low. The implication for us really is that if you are a modeler, especially if you're coding a transport equation for progress variable, you can actually choose the ones that is much easier to code, which means that in reality, the fluctuation is not going to make a huge difference, especially for our approach, which is based on the conditional fluctuation. So that was one thing that we found, and then obviously we had some further development to propose something else. So one of the things then, sorry, I just a little bit rush here again. So what about the PDF and what about the JPDF here? So the question then is the question 3, and then this is a tough and ongoing task that my one of the PhDs currently working with me is working on, is that eventually, once we have this hypothesis, the next question we have is how do we have this PDF and how do we integrate it together to make a routine that actually calculates the chemical source term. So in this particular case, we did have two DNS data, which one is from Lund, thanks to Professor Bai, and then also we have one from Argonne National Lab from Dr. Xu that provided this data set to me with different characteristics. So we're testing, first of all, just to see what are the presumed PDF and then has been used in this particular case. Most of the literature would use beta PDF, and then some of them use clip Gaussian PDF. And we're just to see how good of a representation of this particular flame is in this particular case. what is the PDF that is most relevant to this particular flame, and then in this particular case, we are evaluating what's the joint probability density function of it. So this is, again, a little bit ongoing hypothesis test. So basically, the framework of this particular set of research we have is that can we move alongside every single steps of our development through hypothesis testing, through theoretical validation. So, and then there are a few things we want to be working on as well at the moment, is that we need to work on a proper improved version of presumed PDF because it's in submission at the moment. We're understanding what is the effect of assuming that it is statistically independent on particular flame. And then with the joint PDF, can we use something that is a bit more clever? For example, we are trying to use heavy tails, that's heavy tail presumed PDF, because some of the statistical behavior of the progress variable should not align very well with beta PDF. Because for example, for a flame in premixed states in any grid, the most likely to happening progress variable is actually 0 and 1 because it's either not burn and burn. It's only a small region that has a bit of distribution between 0 and 1 because that's where the flame is actually burned. But that characteristics is not very well described by a beta function because if you know beta function, it's actually not going to achieve infinity high on the tails. So that's why we want to employ heavy-tailed PDF for this particular case. And for hydrogen fuel, which is a bit of what we are doing currently, is all our work are, say, Bilger mixture fraction definition. And so one of the things we always had a question is that actually a good definition for it? We don't know. But one of the idea we want to try is how about we actually input a massless progress variable transport that follows a Brownian motion where every species diffusion is actually referenced to this massless progress variable that was transported through the field that actually describe the mixing itself. Then we don't have to be fixated on a specific atoms. For example, for carbon fuels, we're just mostly looking at the carbon atom to do this. But this is also a bit of testing that we're currently doing, and then hopefully we will have additional results here. Lastly, but not least, it's the research initiative we have. We do have a Hydrogen Center of Excellence just for the research particular. So in our province in Canada, we are trying to upgrading a power plant that is relevant to methane burning. But now we want to make sure that this is able or capable to burn together with methane and hydrogen blend. And this is through our collaborators from UBC. So we're trying to do this active flow control for flashback from Dr. Sina Kurhak's group from UBC. And we're trying to see the differences between blending of this particular burner, what will be the effects of flashback. And there are some preliminary simulations we did for other type of swirl burners just to validate what's going on with the flashback with particular model that we're developing. And then last but not least, there are further development of how do we actively flow control with these models that we have developed and to do industry applications. The last bit was probably a bit interesting to me, at least. So when I was a PhD, we did this thought about, okay, my housemate was in cancer research. So he was trying to identify what is the mutation direction of a specific gene in the location of this particular tumor. So I was saying that I was doing exactly the same for chemistry. And then how do we actually identify what is the manifold in that particular time of the period I was doing TGLDM? To identify where does this water and CO2 is going through this flame for a conditional sense. So then we did this collaboration, kind of weird collaboration to think about maybe RNA works exactly the same way where RNA would cluster together in a trajectory and then it would go through this development through the cancer cell. And this magically kind of worked together. The idea here is really for me, in particular as a junior faculty, I thought combustion science is quite fun. And then in this particular case, we can actually apply to this theoretical checking to a lot of other fields that we are doing. So I hope this is somewhat interesting to the audience that came here, and I want to thank to my sponsors for the research, and then thank to my current active collaborations through the universities, and then my current members in my team, as well as my past members, has worked on various topics that I've just introduced here. So thank you very much for your time, and then I hope this is somewhat interesting of a combustion model or combustion approach. Thank you.
Thank you very much, Leo. Thank you very much for this very nice talk. I would like to see if there are questions from the audience to start. Maybe I can start. There is one from Arthur. Arthur? Yeah.
Yes, can you hear me?
Yep, we can.
Yeah, right. Thanks for the presentation. I was just wondering, when you apply PCA, have you identified potentially a third PC which might carry some variance in the data or might be relevant to characterize what you're investigating?
In this particular case, because we are only looking at a partially premixed flame, so for Sandias wall burner, previously we have done some testing with bluff body dataset. We have found whenever there is a bluff body, we do probably want to consider something that is temperature related, which means in the idea of principal directions, we probably, for conditional variables, we probably need something like total enthalpy, or maybe something that is relevant to the heat loss that we can cover. In this particular routine, though, we thought that because the fluctuations that we found is small enough in the range of the data set, and when we reconstruct it, the accuracy is in the range of maybe 2% of the fluctuation, we do think that two direction is good enough. But as I said, this application of this analogy of hypothesis test would probably more relevant to this test sets, but it's characterized as wall burner from different conditions. But I had a discussion with Kendall as well, is that we thought if you can describe a location of the flame with the mixing, with the progress, with how much heat that was lost, we don't think you need additional conditional variables or additional kind of principal directions. That's what we thought. Yeah,
Okay.
but could be wrong. Yeah.
If I may have a second point.
Yeah.
You mentioned a massless progress variable for
Yeah.
H2 combustion.
Mhm.
Would it be a passive scalar, or how would you interpret it?
I would interpret it as a passive scalar because you think about that there is ink. Well, obviously this is in development. One of the students is working with this.
Sure.
Is that the idea here was that we would put a massless scalar that just go with the flow, and then it has the diffusive behavior, and it's a passive scalar. So which means it does not. It's like background transport equation that does not go through mass and momentum conservation. And then therefore, in reality, what you think about is it's a water, and then you put a dye in it, and then it diffuses. That's what's the natural diffusion is going to happen in this flame. And then which means the chemistry diffusion should be a reference to this. It's like maybe you put a fraction of the diffusion that is relevant to this. If it's, let's say, hydrogen molecules, it will be a bit faster than this dye. Whereas if it's a carbon-related fuel, it should be relatively similar to this dye. So that's one way of thinking about it. It should be a passive scalar. Yeah.
Okay. Thank you.
Yeah.
Thanks, Arthur. I see Salvatore has a raised hand.
Okay, yeah. Thank you very much for your talk. I have a question regarding. Actually, I have an answer to the question regarding the joint PDF, but I would like to know your opinion.
Okay. Yeah.
No, because we tried already in a study like that I did in Cambridge to actually regress the joint PDF with data-driven method using a machine learning approach. What do you think? Do you think it's a viable option, or it's just I mean, how can this data-driven machine learning, since we have DNS data and also experimental data, we can combine this with data-driven approaches to answer the question on joint regressing the joint PDF.
So I'm not a data person, so I don't know how exactly the techniques works. So all we did was manifold reduction techniques, which is more looking into when we have the data, just to dissect the features of it. But from the building point of view, so what we are trying to currently do is we are tabulating the PDF of a linearity model, just to actually tabulating the entire table. But I see that it could be probably a good approach for data-driven, because whenever I think about data-driven, probably the one thing that comes to my mind, it should be optimized, is just lookup process. Because I see it mostly what we are doing for PDF lookup, if we're building a table for linearity model or modified laminar flamelet model for the PDF. So it's probably a good way to use data-driven methods. But the idea here really is that whether we can use from a set of DNS data to get the PDF and then project it to a posterior flame that we don't know, that part I don't know how advanced the data-driven is. But for us, what I can see is that, yes, for a particular flame, I'm going to build up a linearity model to represent the PDF anyway, which is a huge table. And then that part, we can probably use the data-driven method or some sort of a clever sort of lookup process that a lot of people has been building, I think. So I think we can definitely benefit from there. Yeah.
Thank you.
Thank you, Salvatore. So I see that there is a question in the chat. Alexandre was actually mentioning that in slide 20, you have a PDF graph with alpha and beta parameters.
Mm-hmm.
I don't know if you can go there.
No, this is a specific for mean and variance. So it's inside the beta formulation.
Yeah.
You have alpha and beta, and then it's mean and variance related. Yeah.
Yeah. So, Alexandre, I don't know if you want to add on this question or it's clear. I think it's okay. I don't know if there are other questions. Okay. So I see it's 4 p.m.
Mhm.
I would then suggest to close the discussion here. Thank you again very much for this very nice talk. Thank you everyone for attending, and see you for the next appointment of this series. Thank you. Bye bye.
Thank you again. Thanks for the invitation.
Bye.
Bye.
Bye bye.